All right. Last week we talked, or the week before last, we talked about the site work, getting the approval, getting all of the things that lined up, and assuming you've gotten site approval, it's time to start working on the foundation. So this week we're going to talk about some of the things that go into putting in a good foundation. Just as a reminder, I'm going to upload the PowerPoint, and I have a PDF file I'm also going to put up for this lecture so that you can download it to your computer anytime and go through that. There's quite a bit of terminology that's included in this lecture today. Overview, loads and settlements of foundations. We talked a little bit about this on the site work when we talked about exploration and testing. Types of soils, types of foundations, and how those things come together. In the state of Maine, for instance, we have adopted the California code, which requires us to do seismic testing on our grounds, our soils, just in case of a earthquake. And it's some people, it's a little bit over the top based on our history of earthquakes in the state of Maine, but nonetheless, we are required to do seismic testing on our soils. Try not to read these things too much. I'm going to go through them. I got a lot of slides here to look at. The function of a foundation is to transfer the structural loads from a building safely into the ground. As buildings get bigger and taller and heavier, we need to think more and more about what's underneath the ground to support those. So we're going to be looking at different methods that we can use to support a building. There are some areas of the country where there is no bedrock within reach. We're going to end up putting down piles and caissons to support a building with a foundation on top of that. Types of loads on foundations. We have dead loads. Dead load is just the weight of the building itself. Live loads could be movable furniture, people, anything that can kind of change within the building is a live load, and there are maximum live loads for certain floor levels. Wind loading, inclined thrusts, uplift, water table forces, and earthquake forces or seismic forces. The types of settlement that we may see in a building are either uniform or differential. Uniform settlement would indicate that the building will either rise or fall uniformly across the building and cause very little in terms of structural damage. Differential settlement, on the other hand, is where part of the building might be on a solid piece of bedrock, the other part of the building may be loaded differently on less supporting soils, and part of the building could sink or rise while the other part stays stable, causing some structural damage and, at the very least, wall cracks and things like that that could cause issues. Requirements of a safe foundation. Structure foundation system must be safe against settlements that would lead to collapse. Foundation settlement should not damage the structure, and foundation must be technically and economically feasible. We don't want to spend all our money in the foundation, but with the same token, that's what's going to support our entire building, so we have to look at it from both standpoints. Foundation loads. Again, dead load, that weight of the building itself is just going to stay permanent all the time. Live loads, those moving parts and things that can be changed or moved around. Wind loading. If we've got a 50-mile-an-hour gusts of wind outside, we want to make sure that we're maintaining the stability of the building during those types of wind loads from any direction, whether it's the north, south, doesn't matter. We need to make sure that our building can handle any type of wind load. Horizontal pressures below grade, and those could come from seismic or water table differences. Structural member forces, racking of the building, making sure everything is nice and tight. Uplift, and uplift could be part of your wind load, where we've actually had instances where barn doors have been left open on farms. Wind would come in and actually lift the roof off the building by creating so much internal pressure that those, and with no tie downs, those could actually lift the building right off the foundation. So all of those things, and then of course our seismic loading. Here's an illustration of the settlement of the foundation. We have no settlement, total settlement. These are both uniform type settlements, going down or up or just staying the way they are, and differential settlement, where the building can sink and rise in different locations, causing possible structural damage. Here's a photograph of looks like a swimming or some kind of grate on a sidewalk. I'm not sure what that is, and we can see where this portion of the pavement has stayed the same, whereas this part has sunk in the ground. Could be a frost issue, any type of soil settlement. Might have been some air pockets, didn't get packed down enough. I was walking down the road the other day from the credit union, and I noticed there was a snowbank and the pavement was exposed, and I noticed there was about a consistent 3 or 4 inch difference between the pavement on the sidewalk underneath at the edge of the snowbank and the roadway itself. And I got to thinking about that. The snowbank actually allows insulation. It doesn't allow the frost to penetrate into the road surface because it's got the snowbank on top of it. Thereby, the snowbank stays where it needs to be. And because of the frost action, the road had actually shrunk and condensed down and actually dropped consistently down through. So having an area that's insulated or frost protected in one area and not frost protected in another is going to cause those types of differential settlement. So in addition to just the soil's capabilities, frost is something that in this part of the country we also need to think about as part of that differential settlement equation, and making sure that we're below frost line. In this area we're looking at 4.5 to 5 feet depth to get below frost. Other areas of the country maybe much less or none at all, but certainly designing to your climate is another important factor in your foundation. Types of soil characteristics, we kind of went over this a little bit last time, but here's a definition. We have rocks and soils. Soils are defined as particulate earth matter, and we can have boulders, which are too large to lift by hand. Cobblestones, think of these as cobblestone walkways, are stones that could be lifted by a single hand, will kind of fit in the palm of your hand, would be referred to as a cobble. Gravel aggregates are stones that are just clean and larger than 6.4 millimeters. Sand is frictional, it's very drainable material, so we use sand in a lot around foundations. It doesn't absorb moisture, it allows the water to go through. Silt, frictional, low surface area to volume ratio, sizes vary, and very similar to your silts are your clays, which are cohesive, fine-grained, high surface area to volume ratio, very small, and these are types of soils that will actually hold moisture and expand and contract, so they're not great places to put a foundation if they're going to be exposed to frost or water. And to give you an idea, if you're in a clay area of soil in the summertime when it's hot, it's very hard and brittle. You can't get a shovel into it or a spade, very tough to dig. But at the same time, in the springtime, when there's a lot of moisture and snow melt and that starts to thaw out, all of a sudden it becomes soup. I mean, it's very difficult to clean up. So it's just that variation between temperatures and water control that makes silts and clay a difficult material to put building structures on. We do it in this area because we have so much of this material, but it's important to also include good drainage material as backfill into our foundations to make sure that they work well. And then we have our peat soils, which are basically organics material. Any type thing that's rotted wood, anything organic, grasses, trees that have rotted and become soils are not good foundations or foundation support systems. We need to clean that off and get it out. And there is a classification system for these types of soils. Here we see some illustrations. We see some porous sandy material. Over here we see some clays, and there's that sloppiness with the water in there, and it just becomes a mired pit. And same down here. Here's some sands. One thing about sand, it does have good drainage, but it also is something that is tough to maintain the shape of as far as digging holes. We've had contractors that workers that get buried by this stuff sliding out. So you can notice that in the silt and clay we don't have much of an angle of repose, and we'll talk about angle of repose here in a minute. So we can kind of cut right in there and it'll pretty much hold itself. When we talk about cohesive soils, those are soils with a little bit of moisture. If you can take a little bit of that material and squeeze it in your hand, and when you open your hand up it maintains its shape, that's what we would refer to as a cohesive soil. Whereas sand, if you do the same thing and it's dry, even if it's a little moist, you squeeze it in your hand, when you open it up, the sand will kind of fall apart. Those are the differences. So the angle of repose that we need to maintain is, oops, where am I going here? There we go. Properties of the foundation, we have the strength, the load-bearing capacity, the difference between the crystalline rock, 12,000 pounds per square foot, as opposed to different types of soils, 2,000 to 3,000 pounds per square foot. Stable under loads. There's things like creep, shrinkage and swelling. Concrete will shrink and swell as it cures. It will move. So even though it has a lot of tensile strength, it doesn't have a lot of compressive strength, I should say. It has a lot of compressive strength, but its tensile strength, its ability to stretch and move, make it less desirable, so it will crack. Drainage characteristics, making sure that water can drain off the soils. If we're in, it's not just to keep it from water penetrating the foundation, but if you've got a lot of water in your building site and it freezes and thaws a lot, you're going to end up with some problems with your foundation, especially if it's not down below frost level. Soil properties, your subsurface exploration, we talked about that. I will mention particle size distribution and the liquid limit and plastic limit. These are tested in the lab. The liquid limit is the soil's ability to hold water without becoming, at what point does it become unstable? In other words, it'll start flowing away or just slumping. The plastic limit is just the opposite. At what point, when we remove moisture, does it become hard and less pliable? So those are all things that we want to test into the foundation itself. Some excavation requirements for every building. Topsoil organic matter must be removed. We generally set this material aside because it's valuable in our landscaping later on. The required depth, the type of machinery now that we're looking at to get in there. And we look at excavation must be protected from caving in. And we do that with either benching the soil, or sheeting, putting soldier beams and lagging and sheet piles and slurry walls, or some type of bracing where we've got rakers and tiebacks, and we'll look at some illustrations of those. In addition, we may be in an area where the soils are wet and maybe near a water source where we need to dewater the site. We may have well points, which are basically just drilled holes around the site, and pumps that allow us to keep water from entering the site with the while the construction is going on. And even afterwards, we don't always keep the well points in there, but we're certainly going to put some kind of a drainage system that's going to work well. But sometimes your water table just gets up above your foundation level and it makes it difficult to work, so you may have to dewater the site in order to make it work. Different types of equipment. Here's just some illustrations of some dozers you'd use for this earth moving equipment. Then we've got our excavators, your backhoes, your graders, your big excavator down here. If we have an unrestricted site to work in, where we can bench or create an angle of repose outside the surface, and must have perimeter clearance. In other words, if you're building in a narrow site that has another property owner on both sides of you, you may not be able to create that benched excavation or that angle of repose, which means you have to use a different building method. You need to consider bank erosion, water diversion or dewatering, safety. In other words, you got guys working in the pit down in the bottom of that hole. You want to make sure that they're not going to get buried alive. And storage of that backfill, where it needs to go, when it needs to come back in, or whether it needs to be hauled from off-site. These are sometimes very expensive if you're in a site that is difficult to get material into or get it out of. Here's some benched excavation. You can see they've dug this site in benched areas and piled some of this material up with some plastic to keep it from eroding, so somebody can work around this foundation. They don't have to worry about the sides caving in. If they've just dug this down straight, there's a good chance with a good rainstorm or just natural ability to hold its shape, it could cave in. So you have to do this benched excavation. Where you're in a property that doesn't have that, you may end up putting in soldier beams. This is the vertical standard W I-beam or standard W steel shape, structural steel. It gets driven into the ground, and these pieces of lumber will get put in there. This is the lagging. So we have a soldier beam and lagging to hold the soils back as they're excavating, so that there's your foundation. So you have a very narrow level. We've also noticed that they've got these threaded rods. These are called tiebacks that get driven into the soil and anchored to a point where they'll actually hold the wall in place, even with these driven piles down there, just as an additional. And then it has these rakers or crosslot pieces that will tie everything together, and these just get welded in place temporarily. Sheet piling options could be timber sheet piling, steel sheet piling, where these are just kind of interlocked and driven down in the interlocked position. I'll actually show you an example of this as to how it was done on campus recently. And then we have precast concrete sheet piling, which has a grout key that gets poured in just to hold these pieces in place. Whether they stay on the site or they get pulled out later is, a matter of economics. Another method that is used is called a slurry wall. This would be normally seen in something where you have an urban area, a lot of tall buildings, properties very tight. You'll see this down around the World Trade Center, for instance, where the new buildings are going in. They don't have a lot of property, so the method of construction is to kind of lay out the foundation. They use a clamshell bucket to go in and start digging the foundation. Now, to prevent the walls from collapsing, they pour into this excavation a slurry material, which is basically a loose liquid concrete material that doesn't harden. So that holds the sides from collapsing as this is getting poured in. Then the reinforcing cage gets lowered into the hole. It is pumped. You can see this is called a tremie. This little funnel is a tremie that goes down into the bottom of the foundation, and they pump concrete in here. And as they pump the concrete into the bottom, they pump this slurry mixture out of the top, so it ends up with a full hardened cured concrete wall on the inside. So once they're done, then you can see they've got these tiebacks going in to kind of hold it into the soils. They'll excavate this side of the building site, and they end up with their foundation wall put in place, so you could have a building within feet of this area, and they're able to put these tiebacks in and the cured concrete. So it's basically pouring your concrete wall and then doing your excavation after the fact. So it is a method that's been developed for large cities, any area where that you're going to need to excavate below grade for maybe a parking garage or some kind of below grade areas. When the World Trade Centers collapsed, you could see a lot of this construction as they clean things out, where that was kind of a slurry wall down in there, and they've actually used part of that as part of the 9/11 memorial, as part of the foundation of the old trade centers. These tieback installations, they'll use a rotary drill to drill a hole down into the earth's surface. They'll insert these tendons into the hole, which are basically just reinforcing steel, high strength reinforcing steel. They'll fill it with grout into the bottom area. Right in here you'll see they've injected grout into that hole to let it set up. And once it's set up and expands, then these tendons are actually stressed. They're ground down and stressed to a certain PSI and anchored into the wall with these lags and horizontal whalers. Here's some definition. Cross-lot bracing is where we're using steel or even wood, some type of structural material, to brace the walls from inside. This is called cross-lot bracing. We also have a method called rakers. If we're not drilling in, we can put these temporary rakers in place to hold the foundation back until we've got something built in here. And we have the tiebacks, which we just looked at as part of the slurry wall construction. In this case, we've got a fairly narrow, they've benched excavated it, but it's still too steep to maintain, so they're actually spraying this with a kind of a retention material, and then they spray it with a gunite or concrete material to keep the walls from collapsing during construction. So it's a relatively inexpensive method to keep it back if you're in a very deep, and you can see there's a building right next door, looks like a teller. Not sure what that says up there, but it's a teller function. So they're digging this really deep hole right next to an existing building in order to keep things from collapsing and having that other building collapse on you. We need to put some retention in here, so this is just another method to do that. Retention systems depend on proximity to the buildings, other buildings, types of soil you have, water table level, temporary or permanent type of retention system. Maybe it's going to stay in and actually become part of your foundation wall, like the slurry wall. Contractor preference. Some contractors just like doing things one way or another, and cost-wise they're more geared up to do it a certain way. So that's another method. And cost, that's a key consideration to the owner. What's the least expensive way to do it and still maintain safety within the building site and not set back any other parts of the building construction. Dewatering options. Process of removing water and or lowering the water table within the construction site. Purpose is to provide a dry working platform. If the water table is above the working platform, the options are to keep the water out, let the water in and remove it, or a combination of both. And in our area, most of the time we're into a combination of both, because water will find the path of least resistance just like anything else, and if there's a crack somewhere, it'll find it. And a lot of times it just percolates up out of the ground, so we end up with that ability. So here's our water barriers. We've got a water barrier here. This line indicates our water level. So we've got an permeable layer in the bottom, a barrier on the outside. We need to keep that water out. Barrier must reach an impervious strata, which is this indication down here, impermeable layer. Types could be a slurry wall or sheeting with pumps, and it must resist hydrostatic pressure. With a lot of water on the outside of this foundation wall, there's a lot of pressure increase in that, because it almost becomes like a live horizontal live load that wants to push those walls in. So that needs to be taken into consideration also. A building consists of a superstructure, a substructure, and a foundation. The two types of foundations are either shallow or deep, depending on whether the load transfer is in deeper depths or shallower depths. The soils need for those two types, the soil strength and the groundwater condition, the foundation loads, the construction methods, and the impact on adjacent property are all key factors. Shallow footings are column footings without or with tie grade beams, individual or combined wall footings, slab on grade, raft, more like a residential style foundation. Whereas a deep foundation could include caissons with or without sockets, end bearing or friction piles or pile groups, zone of influence made of concrete, regular site crest, or steel or wood. We'll take a look at those here in just a second. Here's our definition: superstructure, anything above the grade; substructure, any usable space below grade; and then your foundation, which is what is supporting all this material. And what it's showing here are some caissons with a footing constructed with what's called a belling bucket. So it actually drills holes down into the ground when it gets to the bottom, and it actually can flare out its bottom and start excavating the soils in a larger cone type shape so that it gives it more holding power. Primary factors affecting foundation choice: subsurface soil, groundwater conditions, structural requirements. Secondary factors: construction access methods, how easy is it to get to the site; environmental factors, am I going to be draining some wetland; building codes and regulations, impact on surrounding structures, construction schedule, and construction risks. I lived in a neighborhood one time where they were doing some construction and it required blasting. And they went around to the neighborhood and let everybody know that there was going to be blasting going on, which was fine. Unfortunately, in that neighborhood, apparently the ledge or the underground was all connected in one area. So when they did the blasting to open up the ground, it was actually created such a vibration impact, and that ledge underneath was actually continuous all the way back to the other structures. So some people ended up having their foundations crack and their walls crack from this violent transmission of vibration through the ground. So there was some litigation, let's say, going on with people to get their foundations fixed because of this construction. So those are things that need to be considered. Sometimes the contractor can't help it. They don't know where that continuous piece of granite or bedrock is below, but if it's connected to other buildings, certainly that vibration can transmit. Shallow foundations require suitable soil bearing capacity, undisturbed soil or engineered fill. And this is kind of important because if you excavate for a foundation, you never want to dig lower than what you need to, because undisturbed soil has the best bearing capacity as opposed to backfill. If you dig down one part of a foundation to a point where you're going to set your footing for your foundation and leave it alone, but on another side you dig a little too far down and you have to build it back up a little bit with some fill that's brought back in, it's never going to get compacted to the same amount as the undisturbed soil, because that stuff has been sitting there for many years, hundreds of years, and it has compacted pretty much to its full amount with all the changes in weather and whatnot. So always excavation to undisturbed soil. Basic types of configurations are column footings or wall or strip footings. The wall or strip footings are what you see in residential construction, where they're pouring a footing around the perimeter of the building and putting their foundation wall on top of it. Generally, the footing is about twice as wide as the wall itself. If you've got an 8-inch thick wall, you're going to put in a 16-inch footing, depending on what your soil bearing is, but that's normally the configuration. Here we see a combination of spread and strip footing, where we have probably what are going to be some column locations along the building here, so they've widened out their footings for the columns, and also put in a strip footing connecting these that they're going to pour their foundation wall on top of. So we can see our reinforcing steel coming up that's going to lock into the concrete wall, but also these column locations that are going to lock into these areas where we're going to have a steel column probably on a base plate that's going to support the sides of the building. So this area not very deep, so it's probably in a less frost resistant area, so not a very deep foundation. Shallow foundations can be, if you're doing a shallow foundation and on a sloped area, you may want to step the foundation, and I did this in our home. One of the things I would have done differently now that I've seen it is put some kind of control joint to make it crack, because normally with the weight of your building on top of this is the weak point where your foundation is likely to crack, and you'll end up with some kind of a, it might be just a hairline, it's not going to cause a problem, but it's a lot better if you could put some kind of a control joint there and say, I want that to crack right in on that spot. And these grade beams, this is kind of it's a little out of scale, I think, is what I'd say. We don't see this too often, but there are ways to kind of put things in on sloped areas. So thinking about shallow foundations on sloped sites, there are some methods to take care of that. Just some examples of shallow foundations. Slab on grade SOG with thickened edges. We call this a haunched slab. And you can see that these got these tiebacks here that are holding the formwork up. So the concrete is actually going to pour up against this area. And what they've done is dug out a little bit deeper around the edge to put this in. So your foundation may be 4 inches thick or 6 inches thick out here, but when it reaches the edge, it's going to thicken to maybe 1 foot thick. So it gives it a little bit more bearing capacity and allows it to hold itself up a little bit better. We use these in this area quite a bit. Rather than just pouring a 4-inch slab straight across and putting our building on it, there's a better chance of it cracking around the foundation when you do that. If you haunch the slab or create this thickened edge, it actually gives it a little bit more bearing capacity and the ability for the foundation to hold up a little bit better. So if you're building a garage or just a home with a slab on grade, that thickened edge is kind of a nice thing to add in there. Deep foundations. And there are two types of supports that we'd put into a deep foundation. There's the caisson and the pile. The caisson is drilled and then poured with concrete or whatever material. And you can see this is a caisson that's used what's called a belling bucket to make it wider at the bottom. It can be just a socketed caisson that's straight down. The difference between them, caissons are always drilled and filled, whereas piles are always driven. Could be steel, could be wood, could be precast pre-tension concrete. These are just driven into the ground, either down to the bearing area down here at the bottom where this might be bedrock, or a friction pile where they drill them down enough until there's enough friction on the sides to support the building and not having to go all the way down to bedrock. The caisson installation sequence is a hole is drilled with a large drill rig. The casing is installed, and sometimes they maybe just fill it with concrete, but typically you're going to put a casing down in there. There may be a bell or a tip enlargement at the bottom that would widen out to create more of a footing, and then the bottom inspected and tested to see what's down there. They'll drop something in to test the support requirements, and then it's reinforced with steel, reinforcing. Concrete is placed. Sometimes that casing is removed. And here's a photograph of them drilling some caisson material into this area, and then they'll drop in reinforcement. You can see the drill auger over here. Other types of drill augers here, one may be for soils, one may be for going through stone. In any event, they're going to start putting these things in place. End bearing piles and friction piles, I kind of mentioned that just a little bit, the difference between the two. And the types of pile material can be steel, concrete, wood, or a composite. Now this following photo sequence was taken at the site of the Nashville Coliseum, 67,000 seats, had deep foundations, so it's got 3,500 driven piles. They're 12 by 53 H piles. 12 indicates the, this is like an I-beam or W-beam. A 12 indicates the size of the steel from flange to flange, top to bottom, or the height of the steel. And the 53 is pounds per linear foot. So it's a piece of steel that's 53 pounds per linear foot. The pile lengths varied from 25 feet to 75. They used 3 pile drivers with diesel-powered hammers. They did 20 to 25 piles per day per rig. The driving tolerance is 3 inches to 6 inches. So you can see what they've done is clustered these piles in clusters so that they'll cover these with some kind of a plate for bearing capacity, and these are probably at a location of a column or some type of support structure that's going to take the main load of the building. You can see these are all in place and have been cut off. These are in the process of still sticking up above the ground. They haven't been cut to level. Now here's a definition I pulled out of the internet for angle of repose. And basically it's just this first sentence. The angle of repose, or the critical angle of repose, of a granular material is the steepest angle of descent, or dip, relative to the horizontal plane which a material can be piled up without slumping. So if you were to take a bucket of sand and put it on the ground and pile it up into a cone, what is the maximum angle that needs to be before the sand starts to slide down or slump? That is called the angle of repose. And it can be done not only with sand, but any type of soil, depending on what moisture content it has. What type of angle do we need to put in there in order to keep the soil stable without it slumping? Slumping is a term we use also in concrete. We do a slump test where we take a cone and we fill it with concrete, and then we pull the cone off it upside down, so it's an inverted cone like a dunce cap on a piece of plywood. You fill that with concrete, kind of shake the air out of it, and then lift that cone off, and you tell how far the concrete settles. That is referred to as a slump test. The same thing with this. How much can you pile this material up without it slumping or moving naturally? And what that angle is what that angle of repose is, as referred to with sliding. So let me just go back. I stuck this in here just because you can see this is the angle of repose out here. They haven't put anything in, but you can see how this angle is. Rather than cutting it down straight, they've got this angle to prevent any type of collapse, and it's well outside the building footprint. So this is the angle of repose. Here's just that grouping. You can see where these have been piled down to refusal, and then a torch has been used to cut these off. They have an excavator kind of hold the top of the steel. The guy cuts it, and then they just lift the excess off. And these are all at the same level, so they can pour some type of reinforced material on the top. Photograph of some precast concrete piles that also can be driven into the ground and then cut off. Just an illustration of cased piles and uncased piles. There's steel, concrete, open-ended, flute tapered, compressed base. You don't really need to memorize this stuff, but it's just an illustration. Seismic base isolation in areas where there could be some earthquake activity, any type of area where the earth may shake by itself. And not to say we haven't had earthquakes up here, but in doing that in large buildings, the foundations are constructed with what are called base isolators, and these are basically steel plates top and bottom with layered rubber type material in between, so it actually allows the building to move on top of that foundation without causing any structural damage. And these are designed for a certain amount of displacement left to right. So you might see these in the bottom of a foundation from the top of the pile or casement or caisson to the bottom of the steel. You may see this rubberized material that allows the whole building to kind of move uniformly without causing any damage to the support of the building itself. Retaining walls. Retaining walls are put up to hold earth back, maybe keep some water out, and they can fail. The type of failure could be just a wall fracture, or they could overturn, they could just flip over, they can slide sideways, or they can be undermined. Those are the three failure mechanisms, actually four if we count the wall fracture, but most common it's overturning, sliding, and this overturning could happen over a number of years. You may drive by an area that's had a retaining wall up and you see it's kind of leaning. It's just the number of years. There could be a road up here with traffic running across it. Eventually those things may fail, so they need to be reinforced. Retaining walls, design elements to prevent failure. One thing is certainly a tapered wall structure. Makes it less likely to turn because the wider this gets on the bottom, the stronger it is and less likely it is to work against the soils. Water removal using crushed stone in behind. So relieve water pressure, crush stone and weep holes. Weep holes might be just a drilled hole through here that allows water to escape from behind, because if that freezes and thaws, it's going to cause some movement. You got a cantilevered footing down here that sets back into the opening further with reinforcing steel that's tied to the wall, which is going to help prevent this from overturning or moving at all. And then to prevent it from sliding, we put a keyway in the bottom to prevent that from slipping sideways so it doesn't just fall along. So generally you put a 2x4 or 2-inch, or be a 3.5 by 1.5 2x4 in the footing, remove that and then pour on top of it so this key keeps it from sliding sideways. All good methods for maintaining a good retaining wall. We've talked about structures below ground subject to penetration of groundwater. More extreme if you're already below the water table, if you're near a lake or water area that's just going to have a wet area constantly. Two basic approaches are waterproof membranes, drainage, or both, and generally we look at both of these. Waterproof membranes can be just plastic sheets, asphalt coatings, cement plasters or admixtures, bentonite clay, and these can be all sprayed on the outside of a foundation wall to keep them out. Accessories are a protection board, which could be just a drainage fabric on the outside, and a water stop. Water stop is generally a rubber weather stripping type material. It's just a solid rubber, might be 3 or 4 inches wide. So if you have a joint in your concrete, you'd pour this water stop into that joint and to prevent water from getting through, especially on regular control joints. Unit of measure, square feet, and mils. This would be with regard to your plastic thickness. So here we have a normal foundation. This type of drainage method we see a lot in residential, where we've got our backfill, we've got crushed stone along the side, and at the bottom we've got a 4-inch drain tile or drain pipe. Another method is using a drain fabric rather than crushed stone. We just put a perforated fabric up here, or a drainage mat, that goes down into this crushed stone and bed and allows water to flow down and get out of the foundation area as quickly as possible. One of the problems we have with foundations is if you've got a roof overhang up here and water constantly drips off the roof, it's going to cause a washout or some type of erosion along the side, so it would allow water to sit in this valley for longer periods of time and actually get into the foundation. So keeping the slope away from your building so that water that's falling off the roof is going to drain away quickly rather than getting down into the foundation is another good method, and sometimes this requires some maintenance. If you start getting little ditches along your roof line, you want to keep those filled in with stone or something that's going to keep the water off, or even putting, you know, some type of drainage mat there that will keep the water from getting along the foundation will help. Here's a photograph of some drainage mat material that goes up against the foundation wall and just allows water to quickly escape from the edge of the foundation wall and get down into your drainage fabric. Another method is just damp proofing. We're putting this material on the outside and putting liquid asphalt on it. Not sure what this block material, but we don't see too many block foundations up here anyway, so just foundation design for optimal cost. Again, it's just a matter of looking at your site and determining the best way to put it in without causing any major issues. Now that's the end of the slideshow. I got one other thing I want to show you. Let me just hit click to exit. Okay, I'll close this right out. This other thing, it's a PowerPoint presentation, and I want to go through this because it's something we actually did on campus. I'm going to look at this in full screen mode. And I start out with this wind turbine foundation. Of course, the university is quite big right now in wind turbine foundation construction. So this is just a anchor company, this Williams anchor bolts, high strength steel. They get poured into concrete. When you look at these windmills that are setting up on mountains like in Mars Hill, from a distance they look like just toy windmills, but you get up close, these things are huge, and they require a lot of reinforcing and good foundations to hold them in place. So in this case we're looking at an anchor bolt that's in a plastic sleeve that they sell, and I'll just quickly look through this. You can buy them in all different sizes, but these are the methods. Here you can see a foundation for a windmill going in place. And all these anchor bolts around here are down in the concrete. The different methods are, you can see these are filled with grout, and as they tighten these threads down, just like any type of anchor bolt, these sleeves actually expand out into the mix and give it more holding power. This is a simple corrosion protected anchor. This is an enhanced protected anchor, and then we have multi-strand anchors that are into this box method where you might have a bolt connection on the top, but these are strands of high strength steel that get pushed down into the epoxy mix or the grout, and as they get tightened up with hydraulic devices, they expand out in the bottom to give them more holding power, and up here they've got these wedges that hold the cables in place. Again, corrosion resistance is a big thing, so they sell these in all different types. We refer to them as Dewey Dags. We even have a hydraulic test jack that once these are in place, we can put this hydraulic jack on it, and these are designed to hold to a certain PSI before they would pull out, probably well over designed. So if they can put these hydraulic jacks on them and test them, that's one method of being sure that their anchors are in properly. Here we have some different types of epoxy and whatnot in this cage assembly. So we see these reinforced materials being put down into a hole in the ground. They'll get filled with concrete and then tensioned to a certain amount. So we did this on campus. This was pictures that I took from the Advanced Engineered Wood Composites. They call themselves something else now, but we're going to build a structure on this that's already there now that goes all the way up to the end of this parking lot. You know, we got a new drive coming in, and right in this area right here we're going to put a big foundation that goes down about 40 feet in the ground to bedrock, and it's going to get drill anchored into that bedrock, and we're going to fill it with a concrete. So at the time before construction, I set this camera up, and you can see there's our construction trailer. We have out here what's called a flammable storage building. We need to move that. And it holds, you'd think it holds gasoline or oil. It actually holds aquaculture samples, basically pickled fish in grain alcohol. So it's highly flammable, and that's why it has to go into this building on the outside. It has its own fire suppression system. It's on a slab. We needed to lift it up. So we're getting into winter time here now, and what you can see here that they're actually placing these steel sheet piles in the ground because they're getting ready to start excavating for this foundation. This is prior to us arranging for, we needed to remove all the samples, store them temporarily, and then move the trailer and then put all the samples back in. It was a real pain. I was an assistant project manager on this, so I was fairly close to it. So here we see some of the sheet piles are in place. We had the trailer come in to unload all the samples, put in the trailer, and then move it. Things got a little snowy for a while, but I think at this time we were moving samples in. Then we had the state, the largest forklift that we could find in the state, picked this trailer up, laid down some plywood, brought it over, and placed it on top of this new foundation to get it out of the way. So now the trailer's gone, we're going to start putting these sheet piles back in. So we're drilling these down, or pounding these down until they couldn't go any further, right down to the bedrock. Once we have all our sheet piles in place, we're going to come in and start drilling test holes to see where our bedrock lengths are. We're going to drill these down to determine what the excavation depth is. And we're going to drill a whole series of holes. It was kind of interesting when they were doing this, because as they got more and more holes drilled, we could see, once they drill in one, you'd see water squirting up out of another one, so it was kind of cool. You can see this pattern of holes that they're drilling to get a good profile of what the bedrock was underneath. Now, why was that necessary? Because this had never been done before. The structural engineer needed to know how to design his concrete reinforcing, and this was the best way to determine how we were going to design that, by drilling these test holes and determining what the soils were underneath in such a close pattern. This is extremely a lot of really heavy torque is going to be put onto this foundation. You'll see in a second. Here you can see I'm drilling. You can see the water that's kind of bubbling up out of these other areas as they're drilling, but we're getting a good profile. So just another angle. You can see my camera was setting right up here in Murray Hall. So we go through it, and now we've got all our holes done and our profiles are ready. We're going to start excavating out of this site. So they start excavating. They still had some sheet piles to put in here because they left that open so that the drillers could get in. Continue excavating. They're excavating right to the sheet piles. So we're creating this basically wall around the outside. They've got some welded steel reinforcing along the perimeter, and they're just digging down as far as they can. It gets down to the point where they're pretty much stretching it. As a matter of fact, they had to lower a mini excavator down into the bottom at one point to allow them to get to the site. And here the guys put a railing up around here to make sure nobody fell into the pit. We actually had some snow coming off, and some of this material, you can see they were drilling into the bedrock and actually exposing some of that material on the outside. Now you can see, because it's middle of the winter, they actually had these temporary roof structures brought in that they could set over the top of this when they weren't excavating, to protect the hole and keep it from filling up with water and snow. Down here we've got a close-up shot of them drilling with these hydraulic rams into the bedrock and excavating the excess material out of the bottom. So this is about 30 feet down in the ground right now. These guys are, you can see the water pump, it's pumping the water out. They're actually cutting into the stone down here, and they're going to drill that and put some anchors in to actually pin the foundation right to that bedrock. Just another picture of them dewatering. Now, what we've got now is, that's the giant vacuum, the guy standing around watching it. Now we're starting to pour the first lift of concrete in. So we've got our concrete trucks showing up one after another. They're pouring this at about, I think, 4 feet at a time. This conveyor just brings the concrete out, drops into a chute, goes down, and they have a guy down there just directing it, and there's a guy up here with a radio control that can move the conveyor one way or the other. You can see he's moving it back and forth. I'm not sure where he's probably standing over here with his little radio controls. Down here in the pit, the guys have got reinforcing steel laid across. You can see these anchors that are sticking up between the reinforcing, so these will all get poured in place. Again, just continuously building this up level by level, and just pouring more concrete. This went on for weeks. You can see the concrete coming out of the truck and being put into the conveyor. Notice that we've got this gentleman here. He's got SW Cole in the back of his shirt. He is testing the concrete to make sure it meets specification. He does this on a daily basis. Every time there's a pour, he's out there testing it with concrete cylinders, and we'll learn more about that when we start looking at concrete. So just another, they're getting up to the top now, so they're actually pouring this in. As they do, they just keep tying more reinforcing bar into this and putting more things in place. This is the cage. You can see there's a ton of reinforcing. They actually had to leave some spaces open, and the guys had to spread the reinforcing bar apart so that they could get inside it. Here we've got, now we're getting up above ground. We're putting in these metal formwork pieces that were specially designed for this project. And here we are pouring it up even further still, and getting up to the very top. And even this isn't quite done. But now they've pulled the formwork off. This is basically the base. And what we're building up here on the top of this is where they're going to hook the windmill blades on to go out to the side. So this is actually an older one. Let me just, I'm going to minimize, actually I should bring this open almost. I just want to show you one other model that I had that I thought I was just in there, but it was, I'd taken it out so I could publish it on Blackboard. If I go to my week 5 and just pick this one up, and I'm just going to click right down to this one. I wanted to show you, this is what the foundation, so this was pinned to the bedrock as it comes up. It had a shoulder coming out. This is what actually sticks up above ground, is this little ledge, and here's that bolt pattern. This is what they're going to hook their windmill blades to. You can see how this is set up, and there's actually a door in the back that you can walk into with a set of steps down. So when you're hooking a windmill blade onto the end of this piece, you can actually have somebody inside holding the wrench for you as they're bolting this on to tighten up the blade. So these blades would come in, they hook a plate to them, they have different hole patterns so that they can put these into the concrete in different methods for different sized blades. So these base plates are set up, they put the rods through, and then somebody on the inside would tighten those up with a wrench. If we look at the next slide, which is, zoom in and out, how do I get to the next one? I'll just go here. So this is, if we look at this, this is, I pulled this off the drawing, but this is the reinforcing that is in this piece. So you can see how much reinforcing steel is in this concrete, to the point where the aggregate needed to be so small that to make sure that it could fit down in between the reinforcing steel. So you can see there's just a lot of steel in here holding this plate in place. And why is that? Because this is, and I'll bring this view up to full screen. This is what it actually is going to be. Here's our foundation, and we have up to a 70-meter blade that they're actually going to be pulling on and pushing and putting vibration on to determine the strength of these blades as they're being tested to use for these large offshore windmills. So the fact that this concrete had to be put into the bedrock, this was why the structural engineer was so concerned about making sure that this was going to be strong enough to take the amount of strength that they were going to put onto these windmill blades. So that's just a little aside on some of the things that I've dealt with site work and putting in foundations. It's a little off the beaten path when it comes to regular foundations, but I think all of the theories that can be kind of compiled into this one area of construction. So it's kind of interesting, but it did take a lot of time for this one. I don't know how many cubic yards of concrete went into this. So that's it. I'm gonna put these 2 shows up online. Hopefully it'll hold them. They're about 6 megs a piece, and I would download those to your computer and just review. We'll have a quiz on that next week. This week we got a quiz on the previous week, which was on some of the drawing items from the rec center. So with that, I will let you go. I think that's enough for the week.